Welcome to Physics Can Be Fun with me, Stephen Thomas. Today we're going to determine the power of a small water pump. Now the small water pump is inside a bucket, inside this crate. Here we have a bottle and we are going to pump water into this bottle using our pump. So when I switch on the pump, do you see how water is pouring into our bottle? And that is what we're going to do. And we're going to at the same time measure the wattage or power of this pump as it pumps the water. And it says 3 watts. 3 watts to pump the water into that bottle. So I'm going to switch that off. And I'm going to let the water return into the bucket. So I hope we get the idea. Now, let's answer the questions that I've posed on the board. First of all, first look at the wattage written on the pump. So we can read it on the pump, or we can go to the box of the pump, and on the side it says that this is a 5-watt water pump. So 5 watts is the power of this water pump. We then go to the second question. Plug the pump into a power meter, and what does it read? And it reads 3 watts. So it says when we actually measure how much power it's drawing on this power meter, it says 3 watts. So already we're seeing there's a slight discrepancy between what the box says and what the pump actually does. Now, we're going to time how long it takes for the pump to pump 2 liters or 2 decimeters cubed or 2 kilograms of water, because 1 kilogram of water is equal to 1 liter. A liter weighs 1 kilogram. So we're going to pump 2 kilograms of water into this bottle, and we are going to time how long it takes for our pump to do that. So here's our stopwatch, and I've measured from here to the level of the pump is 0.5 meter, and so as I switch the pump on, I'm going to switch the stopwatch on. So are we ready? On our marks, get set, go. And so we're timing how long it takes to pump 2 liters of water with this pump to a height of 0.5 meter. And you can see it slowly rising here. And we are on 23 seconds, 27 seconds, and when we get to our 2 liter mark, and if we look at our stopwatch, there it says 41 seconds it took. So it took us 41 seconds. It says actually 41.91. Let's make it 42 seconds. So how long does it take for the pump to pump 2 liters of water to a height of 0.5 meter? In fact, I'm going to use 41 because I pressed the stopwatch and then immediately pressed the switch. So 41 will be the time in seconds. 41 seconds. So to pump 2 liters to a height of 0.5 meter, this pump took 41 seconds. We'll see why this is relevant in a moment. So, I think we can get rid of this now. We've done our little experiment, so let's get this out of the way so that you can see a bit better. So, 41 seconds. Now, how much potential energy does it represent to raise 2 liters to 0.5 meter? So we're going to use the change in potential energy, in other words, to go from the bottom to the top, or delta EP is equal to mgh. And the mass of the water in that bottle is 2 kilograms times 9,8 times half a meter, and that comes to, because the 2 cancels with a half, and we're left with 1 times 9,8, so it was 9,8 joules of energy were used to pump the water to that height. 9,8 joules. Using our formula for potential energy, or change of potential energy, is mass times the acceleration due to gravity times the height. Mass is 2 kilograms, g 9,8, height half a meter, 2 cancels the half, we're left with 9,8 joules of energy went into lifting that water. Now, that's all well and good. So it took 9,8 joules, close to 10 joules, to lift that water, but we also had to get the water moving, and it takes energy to do that. So we have to ask ourselves the question, how fast did the water travel? So how fast was our water traveling when it was being pumped? Because that also takes energy. It takes energy to get the water moving. Now the simplest way, and there are other methods of doing this, is simply to measure the length of time measure how fast the water moves through this 1 meter long plastic tube. So we can actually use a stopwatch. This plastic tube here is 1 meter long, and we can actually calculate using the stopwatch how fast this water is traveling in meters per second. So let's plug this back in, and then I'm going to use the stopwatch to time in seconds, from switching this on, how quickly does it take before the water starts pouring out here. So on our marks, get set, go. And it was 1 second. It took 1 second before the water started pouring out. Watch again. And 1. Watch again. And 1. So we can see that it takes 1 second to travel the 1 meter. So it's the speed of the water, and all the water will travel at that same velocity or speed, is 1 meter per second. I can show you a way we can do it more scientifically, but this for now is a simple way of doing it. Not the most perfect, but it is certainly good enough for now. So how much EK did it take to get the water moving? And the formula for kinetic energy is this. Change in EK is a half mv squared. Half times the mass, which is 2, cancels out again, leaving us with v squared, and v is equal to 1. So what is 1 squared? 1 times 1 is 1, equals 1 squared, which is equal to 1 joule. So here's our answer. The kinetic energy transferred to the water was 1 joule, and the potential energy transferred to the water was 9,8 joules, and therefore we can say the total is going to be 9,8 joules plus 1, which is 10,8 joules. I'm going to just move this a little bit out the way. So here's our water. Let's get that out the way. here is our crate. Let's get that out the way. And here is our pump. Do you see our little water pump? It always feels scary to drop something electrical at 220 volts into water, but there is our water pump that did all the work. And we're going to move our bucket out of the way. So now, what was the total work, non-conserved, meaning there was friction and other things involved, was equal to delta EK plus delta EP. What does delta EK equal to? 1 joule plus delta EP 9,8 joules, and the total therefore comes to 10,8 joules. Now that is the work done by these non-conservative EK and EP. There's friction and other things involved. Let's work out the minimum power that this pump needs to do that amount of work. So power is defined as work, non-conservative, over time. And the work we've got is 10,8, and the time that it took to fill that bottle was 41 seconds over 41. Let's do the maths. So we've got 10,8 divided by 41, and that is 0.26 watts. 0.26 watts. So equals 0.26 watts. And that is the minimum amount of work that the pump does. The minimum power, which this pump must have is 0.26 watts. Power being work over time. Here's the work that it did. Time it took was 41 seconds. Work divided by time gives us our power of the pump. The minimum power of the pump has got to be 0.26 watts. And we've seen that it is only 9% efficient.